All right, so something to note here. The first student will be selected at random, and then that student's going to be taken away. And then the second student is selected at random from the remaining students. So what is the probability that two history majors will be selected? Okay, so these are dependent events because after they select the first student, it's going to change the denominator. And then there's less people there when they go to select that second student. Okay, so it's the probability of A and B, which is the probability of A times the probability of B, given that A has already occurred. All right, because these are dependent on each other, we're going to break out that crazy little formula. And then we have to remember to round our final answer to 3 decimal places. Okay, so the probability of event A, so let's just call this event A, is that they come in here and they select a history major. Well, out of 22 students, 6 are history majors. So that's the probability of selecting a history major. That's probability of A. Event B, though, it's going to change. Remember that little hint, the denominator changes? So they've already taken somebody out of the class. So now your denominator is 21 people. Okay. And if they already selected a history major, now there's only 5 history majors left to be selected out of 21. So this is the probability of event B. So this is the probability of event A. This is the probability of event B, given A has already occurred. Okay, so we're allowed to multiply them together as long as you were careful to make sure on event B you made those adjustments. So you have 6 over 22 times 5 over 21. Okay, so 6 out of 22 is something like 0.27 repeating. It just keeps going, 27's gone wild. And 5 over 21 is 0.23809. And if you multiply them together, you get something like 0.0649. And then we're going to round to 3 decimal places. So we're going to come out to 1, 2, 3 decimal places, put up a wall. The 4 looks at the 9 tells the 4 to round up. So 0.065. Okay. Or if you think about this in terms of percentages, a 6.5% that the first student they select from the class is going to be a history major, and then the second student that they select is going to be a history major, given they already picked the history major. All right, so kind of craziness here. Here's a recommendation. Take these decimal places out on these initial computations, as far as you can. Then multiply them together and take this out a little further than you need to, so that you can always back up and round. Okay, an automobile manufacturing plant produces 32 vehicles today, 14 trucks, 7 vans, and 11 motorcycles. Each vehicle falls into only one of these categories. Plant managers are going to select 2 of these vehicles for inspection. The first vehicle will be selected at random, and then the second vehicle will be selected at random from the remaining vehicles. So they're going to pull this vehicle out. So this is going to be dependent. Hopefully you're thinking about that here. What's the probability that 2 trucks will be selected? Round the final answer to 3 decimal places. Okay, so there's no replacement of the vehicle. So that equals dependent. So let's set this up. The probability that you're going to get a truck is going to be event A. Event B is going to be a probability that you get a truck. And sometimes they use a pipe symbol here to show that there's another piece of this, so that you get a truck given you already selected a truck. So that given is going to help us think about that denominator is going to be different. Okay, so event A, the probability of getting a truck, well, there's 14 trucks out of 32. That's the probability of getting a truck. But think about the fact they pulled a truck out. So now you're going to try to pull a truck, but you've already selected a truck. What's that probability? Well, that's going to be 13 trucks out of 31. So now we're allowed to use that formula that the probability of A and B is equal to the probability of A times the probability of B given A already occurred. Okay, so this is the probability of B given that, this is event B here. Probability of event B given that A already happened. So we're allowed to multiply 14 times 30 over 32 times 13 times 31. And if you do these on your calculators, and check me please, it should be 0.4375 times 0.41935 should be equal to 0.1834. And since they want 3 decimal places, we're going to call this 0.183. Or in percentage terms, there's a 18.3% chance that they select a truck on the first round, and then on the second round, they also select a truck. Okay, probability of an independent event involving a standard deck of cards. Okay, here's your standard deck of cards. Remember, these are your face cards here. Suppose a card is drawn at random from a standard deck. The card is then shuffled back into the deck. Okay, so hopefully when you see something like that, you're thinking now, oh, okay, this is going to be an independent situation. And it's because the card's going to go back in the deck. So the denominator is not going to change. We're still going to have 52 cards to mess with. Then for the second time, a card is drawn at random from the deck. What is the probability of first drawing a king and then drawing a black card? This is event A, this is event B. Now remember, if they're independent and you're looking at the probability of A and B, you can do the probability of A times the probability of B. No worries with that. Don't round they call it intermediate computations. Basically, round your final answer to 4 decimal places. Don't do any pre-rounding, is kind of what they're saying. Okay, so the probability of event A is drawing a king. Well, we know drawing a king, there's 4 out of 52. The probability of event B, once you put your king back in, is that you're going to draw a black card. Well, there's 26 out of 52. So half of these are black cards. So 26 out of 52. Okay, so we can multiply these together. We're allowed to. So 4 over 52 times 26 over 52 is going to be equal to 0.7692 times, this is a half. And then we're going to go out a few extra decimal places so that we can satisfy this rounding to 4 decimal places. So this is going to be 0.03846. And you're going to go out 1, 2, 3, 4 decimal places, put up a wall. The 4 looks at the 6, and the 6 says round up. Okay. So that's when you're working with independent events where one probability here doesn't affect the other probability. Just straight up round them together. Well, you'll be happy to know this is our last problem in this video. We're going to stop here. Okay, here's a table showing all 52 cards. A card is drawn at random from a standard deck. That card is not put back in the deck. Okay, that's going to make this dependent. Okay. A second card is drawn at random from the remaining cards. So this is one of those givens, and it's going to be independent because that denominator is going to change. Once you pull a card out, when you start with 52, your next denominator is going to be 51. So keep that in mind. What's the probability that both of the cards are diamonds? Okay, so the probability that you have a diamond, and then that's A, and event B is going to be the probability that you get a diamond given you already got a diamond. Okay, so pause the video and think through how you would go for this. Okay, if you're back, remember the probability of A and B for dependent is equal to the probability of A times the probability of B given A already occurred. Okay, sometimes they'll write it like the probability of B, and they'll do a pipe symbol given A. Sometimes you might see it just shorthanded like that. Okay, probability that the card is a diamond on your first pull. Well, we know we have 13 diamonds out of 52. That's event A. But then pretend one of those diamonds gets taken out. Well, now you only have 12 diamonds, or yeah, 12 diamonds out of, now instead of 52, there's only 51 cards sitting there. So 13 out of 52 is 0.25 times 12 over 51 is 0.23529, and that's going to be equal to 0.05882, and they want us to round to 4 decimal places. So 1, 2, 3, 4, put up a door. That 2 tells the 8 to stay the same. So we're looking at 0.0588. Okay, so basically there's a 5.88% chance that you pull out a diamond, keep the diamond in your pocket and pull out a second diamond. That's only a 5% chance of that happening. All right, hopefully this helps. We'll see you in the next video.